One of the most unique and interesting things about composite structures is their failure mechanisms. However, interesting is usually analogous to complicated. We are all familiar with mechanisms of delaminations, matrix cracking, debonding, and more. But a more pressing question still exists that we must answer. How can you identify damage that you cannot see? More importantly, how can we make sure that we catch it before it leads to catastrophic failure? My research specifically focuses on the substructure damage that can be found on naval aircraft during their launch and recovery cycles. These aircraft often need to decelerate from 150 miles per hour to 0 in under 1 second, resulting in intense repetitive loading cycles. As such, it is imperative that I am able to not only identify, but also quantify the damage within the composite structure for the safety of the aviators. So the question remains, how can I keep them safe by warning them of subcatastrophic damage? This is the seed that has led to the vast forest of decades of research into internal damage in composite materials. Scholars all over the world have tried to answer this question through several techniques such as X-ray computed tomography, ultrasound scanning, digital image correlation, and more recently, the virtual fields method, also known as VFM. VFM is unique because it optimizes both cost and time efficiency, often not seen in other non-destructive techniques, without compromising its full field metrology. VFM has been proven to work on single impact experiments in identifying damage, but has not been used in a repetitive loading scenario as the one I had described previously. What sets VFM apart from all the other tools is that it can be used to directly extract material properties from the specimen, making it essential in identifying not only where the damage is within the material, but also how badly it was damaged. My research utilizes the effectiveness of VFM on composite structures in simulated launch and recovery cycles. Namely, impact fatigue experiments will be performed on carbon fiber reinforced polymer composite plates. Environmental effects will also be taken into account by soaking some of the samples in seawater for anywhere between 2 days to 3 months. Other researchers often measure the area or the size of the damage, but what I will be implementing here is an actual loss of stiffness over hundreds to thousands of impacts under different seawater soaking conditions. This will help me better understand and simulate what happens on an actual naval aircraft carrier. Although there is a lot of work to be done, I truly believe that this research can be revolutionary for developing a quick, safe, and reliable way to find substructure damage and warn aviators before catastrophe hits. Thank you for listening to my thesis pitch. Again, my name is Isabella Mendoza, and I'm here at the Colorado School of Mines.